Now that we know that floating point representation and floating point arithmetic are going to make some changes to our numbers that define our problem, we have to ask ourselves, how will the result change as a result of those perturbations in the numbers and the arithmetic? And remember, at the end of the last video, we had two possibilities. So we had the case of a quadratic polynomial, where we artificially perturb the coefficients by about an amount which is less than 10 to the minus 6. So in other words, maintaining about 6 significant digits. And we found that the roots also maintained about 6 significant digits of accuracy. And so, the answer in this case was really no worse than the perturbation in a relative sense of the initial data. All right. On the other hand, we had the other problem, which is seemingly much simpler, of just taking the difference of two values, the difference between pi and a value which is very close to pi. So those two representations agreed to one another to about 7 significant digits. And then when you take the difference, those digits all cancel out, and so we're only left with 9 significant digits. And so 7 were, we say, canceled due to subtractive cancellation. So even though, you might think, well, 9 significant digits is still a lot, and it is, we also just about lost half of them in one operation, so that's probably not so good. We'd like to figure out what's the difference between these two problems. What can we use to analyze them to know when this is going to happen to us? So let's now think about things more mathematically. So let's define a problem as a function, right? So we have some data, and we want to map it to an answer. And different data maps to different answers. Well, that's a function. So to keep things simple, let's just suppose we have a single-valued function of one real variable for now, and we'll call it f of x. So f is the map from data to answer. All right, and then we're going to perturb the data from x to x plus delta x. And then we know that the answer will be perturbed. You plug in x plus delta x into the function, and then the solution is also perturbed. The result is perturbed as a result. Okay, well, elementary, right? We can find what delta f is divided by delta x is, or we used to call this delta y divided by delta x, right? So this is how we started off in calculus with defining a derivative. So in the limit, right, where delta x is 0, we know that this approximation becomes an equality. But as long as delta x is small, this difference, this ratio here, which is sometimes called a finite difference, is pretty close to the derivative. Just as a reminder, of something you should have seen in calculus, there's this concept of linearization. So if I want to approximate a function f of t, we say that f of t is well approximated by a linear function L of t, and L is defined by f of some value a plus f prime of a times t minus a. And it's a good approximation for t close to a. Right? So, or another way is to look at it graphically. So we have some function, which is f of t, and then we have a value at t is equal to a, and we take the slope at that point from the derivative and we draw a straight line, and we call that L of t. And the straight line stays close to the function for a little while, near the point A. So it's all the same as what I did above, where we have, instead of A, we call it X, and instead of delta X, we have T minus A. So it's the same approximation as the one above using the derivative through linearization. But with all of this, I've done an absolute perturbation. So I took x and I just added delta x to it. In floating point arithmetic, we do relative perturbations. So remember, the floating point value of x, for example, is x times 1 plus epsilon. There might be other reasons that your data is perturbed, but certainly floating point is one. Okay, so if we do that, we plug in the new value of x into the function. We get some f plus delta f, so that's the resulting change. And we compute an approximation to delta f through linearization. So we get this quantity when you make the substitutions into the linearization formula. And then, again, we're going to be interested in the relative change in the answer f. So we have to take delta f and divide by f. Right? So remember, epsilon is the relative change in x. Right? So like in the quadratic polynomial root finding problem, we perturb things by 10 to the minus 6, so we should expect that the answer also has a factor like 10 to the minus 6 in it when it changes. However, there's this other stuff that describes maybe some sort of possible amplification of the error. And it's that stuff that we're interested in, that's sort of telling us when we might run into trouble when we do floating point arithmetic. So we use these. Now we take the approximation part of it out, and we make some definitions. So the condition number is really what we use to describe the relative change in the output divided by the relative change in input. And we have two cases, right? So if we think in terms of absolute changes, okay, so I got ahead of myself by saying relative. We could define either kind of change. Most often we're interested in relative, but sometimes we deal with absolute changes. So when we deal with absolute changes, we just have the derivative, right? Change in output over change in input is the derivative in absolute values because we don't usually care about the sign of it. On the other hand, if we care about relative changes, then we look at the analysis that I did above, and we suggested that extra term that multiplies the epsilon should be our condition number. So one thing to notice about both of these formulas is that the condition number depends on the data and the problem. So for a given problem, there might be some data where the answer is very sensitive and others where it's not. So let's go back and look at the problem of adding numbers. So I did say that we only had one input value, so we have to pick one of the things to be a constant and one of them to be the variable x. So imagine in our example above, right, that x is pi and alpha is the approximation to pi with a minus sign in front of it. All right, so to do the relative condition number, we just compute the things in this formula. So if f of x is defined as x plus alpha, then f prime is just 1. And kappa, the condition number kappa, is the absolute value of x times 1 divided by f of x. All right? So what we see, right, is that the condition number is large. We use this double greater sign to mean much larger than 1 if the result is much smaller than the input. Right? So this is what I said about subtractive cancellation. If you have two numbers which subtract to give you a much smaller result in absolute value, then you get subtractive cancellation. So to go back to our example for a third time with pi and the approximation to pi, what we find, right, is that kappa is about 3, right, that's pi, divided by more or less 3 times 10 to the minus 7. So it's about 10 to the 7. So if you take the log in base 10, it's roughly 7, and that's the number of significant digits that we lost. So that's just a mathematical way to explain what happened to us with subtractive cancellation. More involved example is to look at our polynomial root case. Okay, so of course in practice everything is perturbed, right? All the coefficients are perturbed, all the arithmetic is perturbed. But let's simplify the problem by just identifying one coefficient and pretend that everything else is done exactly. So I'm going to pick the leading coefficient and say, what happens if a is altered in a relative sense? What does that do to the root? Well, remember, the root is a value r such that p at r is equal to 0. So we start with this fact about r. Okay, now we perturb a. We could do this in a perturbation sense, but I'm going to use implicit differentiation, which is a topic from calculus you might want to go back and remind yourself of. Right? But what we're saying is that r is a function of a. Right? If a changes, then the root changes. So that means we can differentiate both sides of this equation with respect to a. Okay, a depends on a and r depends on a, so this first term has a product rule, right? It's dA times r squared plus a times dr squared dA. The second term, b doesn't depend on a, b is just fixed, so we get b times dr dA. And c doesn't depend on a, so we just get 0. And the right-hand side is also 0. Okay, dA is just 1, so I have r squared plus a. Now r is a function of a, so we have to use the chain rule. So I get 2r dr dA. Plus b times dr dA equals 0. Solve for dr dA, right, and we get minus r squared divided by 2ar plus b. And if you go back and look at the formula for p of x, in fact, that denominator, we can rewrite it as p prime of r. Okay, so all of that tells us how to compute the condition number kappa. The relative condition number is the data. Okay, so now x means the data, right? So that's a times f prime of x. Well, that's dr dA. R squared over p prime of r divided by f of x, right? That's the result, which in this case is r. All in absolute values. So we get a times r over p prime of r. Okay, so we might find that kappa is much larger than 1 if p prime of r is close to 0. Right? If that denominator is small, then kappa could blow up. Of course, it could also blow up if a is large or if r is large. But those are kind of easy to spot. This is a little bit more subtle. Now, you might remember about a polynomial that if p prime of r is actually equal to 0, that's the same thing as saying that r is a double root. right? We would just have r minus, or x minus r squared as the polynomial. So if p prime of r is close to 0, that's the same thing as saying that r is nearly a double root. So if you have a polynomial whose roots are close together, you might see a great deal of sensitivity, right? A great deal of amplification in the relative error in the roots of that polynomial. On the other hand, going all the way back to our example, here's a polynomial with two roots that are very well separated, 2.5 and minus 1.25. That denominator isn't going to be small at all. You can work out the numbers, and you'll see that in this case, kappa really is no bigger than 1. And so therefore, there really was no possibility of the error getting amplified in this problem. So you see, we have this tool now of the condition number, which tells us the amount by which the change in the output can grow relative to the change in the input.